Hello, dear colleagues. Welcome back to Physics 161 recitation session. Today we're discussing work, energy conservation principle, energy of the system, energy conservation principle. And I'd like to start with a discussion of some formulas that we are going to use today and in general in physics. So kinetic energy, it's 1 over 2 mv squared. Kinetic energy of the object, V, is the speed of the object. So gravitational potential energy is mgh, where this h is with respect to some height that we assume to be a reference level. So in this sketch, you can see that we assume that this level is 0, and if this height above this level is h, then the potential energy of this guy is mgh. So this is gravitational potential energy. Also, we can store the energy in a spring, and this energy potential would be 1 over 2 k times delta x squared, where x is a spring constant. Delta x is the displacement of the spring. So for example, here we have a stretched spring. So this displacement when the spring is stretched is delta x. So then the potential energy stored in this spring is 1 over 2k delta x squared. Next, new concept of physics, it's work. So work done by the external force on the object, and it is equal to integral of F, which is a force, dot product ds. ds is a small element of the displacement. This is a vector. So, so when the object is moved from position 1 to position 2, then the work would be equal to this integral. So, and we have to integrate the displacement from point 1 to point 2. So today I will show you how to work with this formula. And here is a definition, just to remind you, definition of dot product of two vectors. So dot product of or scalar product of two vectors is a scalar. And the scalar equals to absolute value of vector A times absolute value of vector B times cosine angle between these two vectors. Okay, and next important concept of physics, the energy conservation principle. So the energy of the system, which consists of, which can be expressed in kinetic energy, potential energy, and internal energy. So this energy can be changed when we do when some external agent does some work on the system. Okay, so this is change of kinetic energy, this is a change of potential energy, and this is a change of the internal energy. So here we just need to analyze K final minus K initial, here U final minus U initial. Now a little bit about the change of the internal energy. So the change of the internal energy equals to the friction force times the displacement. So not dot product, but just times. And it is important always to keep in mind that friction force equals to the mu, which is a coefficient of friction, times normal force. So normal force is not always mg. It depends on the problem. So that's why this is general form for the friction force. So okay, let's apply all these concepts and let's solve some problems. So let's start with problem number 1, just to warm up. Let's introduce in general concept of work. So the problem is as follows. A block of mass m, 2.5 kilograms, is pushed a distance d equals 2.2 meters along a frictionless horizontal table by a constant applied force of magnitude F, 16 newtons, directed at an angle of theta 25 degrees below the horizontal as shown in the figure. So we need to determine the work done on the block by the applied force, which is here, the normal force exerted by the table, the gravitational force, and the work done by the net force on the block. And here we have a figure. So let's collect what is given in this problem. Let's draw this figure again. So it is given so that the mass of the object of the block is 2.5 kilograms. By the way, let's draw it here. The problem, the object. So we have this block of mass 2.5 kilograms. Initially, it was here at this point. Then we moved. Some external force was applied to the block. So here is the force, external, which is applied to the block. So the direction is theta with respect to the horizon. So here is a new position, and still it is moving, this object, but it passes this distance d, which is 2.2 meters. And what is given in the problem? So d, distance, is 2.2 meters. So the absolute value of the force is 16 newtons. So this theta angle is 25 degrees above a horizon. And also this surface is frictionless. So coefficient of kinetic friction is 0. And we need to find the work done by the force, by the normal force, and the work done by them. So this external force, which is applied force, normal force, and gravitational force, and the net force. So let's find the work. So first, we need to find the work done by this force. We need to find the work done by the normal force. C, we need to find the work done by the gravitational force. And D, we need to find the work done by the net force acting on the object. So at the beginning, let's consider the work done by this applied force. So again, let's recall this formula, a definition of the work in physics. So the work equals to the integral of dot product of the force and displacement vector. Okay, so what would be the displacement vector, this small displacement? So it's like that, agree? So that would be some small part of the total displacement. So, and if we introduce coordinate system like that, with this coordinate with the coordinate axis x, we can simply express that this ds in general in these terms would be equal to I hat times dx. Okay, and from that we can say that what would be the scalar product of these two vectors? So that would be vector f dot product ds. Now it would be equal just absolute value of vector f times absolute vector value vector ds, which is just dx, agree? Absolute value of I hat is 1. So dx times cosine theta. Cosine theta. And if so, let's substitute now this scalar product into this integral. And we will find the work done by the force F, like that. So that will be the integral. Now, the object is moved from here to here, which means we can say that it is moved from the position of 0 with respect to the x-axis to the position of d, again with respect to x-axis, and this scalar product. So that would be f times cosine theta times dx. So everything, so this is a constant with respect to the varying parameter x. So that will be just f cosine theta integral from 0 to d dx. And this integral is just d. Agree? And so let's substitute theta as minus 25 because it is above the horizon. So now general formula for this work would be f times cosine minus 25 degrees. So it's clockwise with respect to x-axis times d, because integral of dx is just x. So substitute all the numbers and you will obtain that the work done by the external or applied force is 31.9 and units are joules. Okay. So this is the first part of the problem. Next, we need to find the work done by the normal force. Work done by normal force. So let's introduce normal force into this sketch. So here is a normal force. So what would be the work done by the normal force if the object is moving to the right? Well, let's analyze the angle between normal force and the displacement vector ds. The angle is 90 degrees, which means that cosine theta here for them, not theta, but cosine of this angle is 0. That's why the normal force does not do any work here in this process. So since n perpendicular normal force perpendicular to the ds, from that their dot product would be equal to 0. So the work done by the normal force is 0 because work is the integral of this dot product. So the same we can say for the work done by the gravitational force mg. So here we have mg, and as you can see, the object is moving perpendicular to this force, which means that this guy does not do any work because angle is 90 degrees. So mg perpendicular to ds, and from that, the work done by the gravitational force is 0. So in the final part of the problem, we have to find the work done by the net force. So we analyzed all the forces exerted on the object here. That's why the net force would be equal to this value, agree? Because there is only one force that makes the work here. And that is the net force. So the work done by net force equals to the work done by this guy, applied force, and this is equal to 31.9 newtons. So that's the answer for the part D of the problem. So questions, please. Okay, good. Now we introduce the concept of the work into our knowledge. Now let's solve the next problem. And in the next problem, we need to find speed. So here we will work with the kinetic energy and energy conservation principle. So the problem is as follows. A 6 kilogram block initially at rest is pulled to the right along a frictionless horizontal surface by a constant horizontal force of 12 newtons. So find the block's speed after it has moved 3 meters. Okay, now let's collect what is given. So it is given that the mass of the block is 6 kilograms. So initially the block was at rest, so initial speed is 0. Surface is frictionless, so kinetic the coefficient of kinetic friction is 0. So this force now is parallel to the surface, and obviously that will be parallel to the displacement vector ds that we will introduce later. So this angle theta here would be 0. So the absolute value of the force is 12 newtons. And we have to find the speed after it has passed a distance of 3 meters. Okay, so we need to find the final speed. Final speed. So solution, let's start our solution with this figure. Let's draw it here. So we have the object with mass m, it's like that. The force, which is acting from the external agent, is parallel to the horizon. So surface is frictionless. So there is a force acting on the object will move with some acceleration, and it will reach some point here, which is d, the distance from initial to the final point. In this, at this point, the object will move with some final speed or velocity. Okay, so we know that mass of the object is m, initial speed is 0. We need to find the force, oh, excuse me, this final speed. So you can solve this problem since it is relatively simple with the kinematics equation, but also we can apply here the energy conservation principle. So by the way, let's introduce here normal force, just because we are physicists, and gravitational force. Now, energy conservation principle. So the change of the energy of the system, which can be expressed by the change of the kinetic energy in the system, the change of potential energy of the system, plus the change of the internal energy of the system, is caused by the work done by the external agent. So this work introduces some energy into the system, and this additional amount of energy can cause the change of kinetic or potential or the internal energy. So later we will also introduce some heat. That will be thermodynamics, and you will cover that a little bit later. But so far, today we work with the work. So now let's analyze initial and final energetic state of the system. So system consists just of, there is only one block in the problem, so that's the whole system. So initially, so let's consider the initial and final, let's call it energies in the system. So what was the initial kinetic energy of the block? It is 0, agree? Because the speed at the beginning was 0. So what is the final speed? It's excuse me, not speed, but kinetic energy. It's 1/2 mv final squared. So what can we say about the change of gravitational potential energy? So the level is the same, which means that there is no change in gravitational potential energy in the system. So that's why the change of potential energy is 0. And also the surface is frictionless. That's why there is no change of the internal energy in the system. Okay, so the delta E internal is 0. So this is the left-hand part of this equation, of this relationship. Now let's analyze the work. Let's find the work. Again, just to remind you, let's recall the general definition of the work. So F dot product ds vector. So here ds is a small part. So this is vector ds, agree? So the angle between force of the external agent and displacement vector ds is 0. That's why the scalar product would be just F, let's call it dx. And that would be equal just to F times total displacement d. That's the work done by this external agent. So change of kinetic energy plus change of gravitational potential energy plus change of internal energy equals to the work. So let's combine them together, all these formulas, and we will obtain that. So the change of kinetic energy is just 1/2. So K final minus K initial, that would be 1/2 mv final squared equals to Fd. Agree? And from that, we can find the final speed of the object. So it's equal to square root 2Fd over the mass. And the numerical value, when you use all the given information in a given box from a given box, it's 3.5 meters per second. That's the final speed when the object passes this point, 3 meters from the initial position. Okay, and it will move with some speed. Okay, questions for this problem? No? Okay, great. Now let's solve the problem with friction. Now friction would not be 0 here in the next problem. So the problem is as follows. A 6 kilogram block initially at rest is pulled to the right along a horizontal surface by a constant horizontal force of 12 newtons, like in previous problem. So we need to find the speed of the block after it has moved 3 meters if the surfaces in contact have a coefficient of kinetic friction of 0.15. So now we have a friction. So what will happen with the speed? So let's again collect what is given. Again, mass is 6 kilograms. Initial speed is 0. Absolute value of the external force is 12 newtons. Angle between the applied force and the horizon is 0. Not horizon, but surface of the table, so, which is parallel to the horizon. So d equals displacement is 3 meters. And now we have coefficient of kinetic friction, and it is equal to 0.15. We need to find speed in this case. We final. Okay, solution. So let's draw again the diagram with the new force here, which is friction. Now the surface is not frictionless, it is rough. So there is a force applied to the object. So that would be the direction of displacement, vector ds. And here is a position d meters away from the initial point. So here the object was at rest. And here the object is moving with some velocity. Okay, so this distance is d, which is 3 meters. And also there is a normal force exerted by the surface to the object, gravitational force, which is caused by the gravitational field of the Earth. And here is a friction force, which is in opposite direction to the direction of movement. Okay, now let's analyze again this problem with respect to the energy and let's recall the energy conservation principle, like that, like it was in the previous part. It is equal to the work done by the external force. So again, K initial is 0, K final is 1/2 mv final squared. Okay, again, no change in the height, so the same height, the same level. That's why gravitational potential energy is 0. Also, there is no spring here, so there is only gravitational potential energy can be changed, but the change is 0 in this particular case. Now let's analyze the change of the internal energy of the system. And as I said, it is equal to the friction force times total displacement. So this is D. So this absolute value times D. Now, what is the friction force here in this problem? Friction force, from definition, equals to the coefficient of friction times normal force. And in this particular case, if you look at this object, you'll find out with free body diagram and Newton's second law that there is no motion in y direction, which means acceleration in y direction is 0. And that's why the absolute value of normal force equals to the absolute value of gravitational force. Agree? So that is intermediate statement. So N equals mg in this particular case, absolute values. So from that, we can say that friction force absolute value equals to mu times normal force, which is mg here at this problem. So now, taking this into account, we can say that the change of the internal energy is friction force times displacement. Here is friction force, so it's mu mg times displacement. And now let's analyze work again. And work here, since they're parallel to each other, this force applied and the displacement vector. So the work would be equal to work equals to F dot product ds. So that would be just F times D. Agree? Now let's combine this energetic parts and this work. So the change of kinetic energy is 1/2 mv final squared, which is K final minus K initial. K initial is 0. So plus the change of potential energy, which is 0 in this particular case, plus the change of the internal energy. This is mu mg d equals to work done by the external agent, Fd. So from that, now we can express the final speed of the object. So the final general expression would be square root of 2 ft minus mu mgd over m mass. Okay, that numerical value with the given numbers is 1.8 meters per second. So that's the answer. Okay, questions, please. No questions. So now let's solve the part B of this problem. There is a part B in the problem. So all the parameters are the same except this angle theta. So suppose the force F now is applied at angle theta as shown in this figure. At what angle should the force be applied to achieve the largest possible speed after the block has moved 3 meters to the right? Okay, now all the parameters are the same like here, but the force is now applied at some angle theta. Okay, so let's analyze this problem. So given is the same. So just for the recording, let me again summarize what is given. Mass of the block is 6 kilograms. Initial speed is 0. Absolute value of the force applied is 12 newtons. So the displacement in the problem is 3 meters. So now we have again the coefficient of friction, which is 0.15. And we have that when the object passes this point, which is 3 meters away from the beginning, the kinetic energy is maximum. So K final is maximum. We need to find the angle of the force application. So theta is question. Okay, now solution. let's discuss the solution. So let's draw this again, this diagram, the object, friction, the surface which is not frictionless. So there is a force applied at some angle now to the horizontal plane. The object is moved to the right. It has some final velocity here. So the displacement is directed like that. Okay, so distance is d. And also there is a mg vector and some normal force here, which is now would be smaller than mg. I will discuss it with you later. And there is also a friction force again. So initial speed is 0. We need to find at which angle we should apply this force F to reach the highest possible kinetic energy at this position. Okay, now again, let's recall energy conservation principle. The change of the total energy of the system equals to the work done by the external agent. So the change of kinetic energy here would be just K final minus K initial, and that is just K final. Okay, so that's the change of kinetic energy. So change of potential energy is 0 because level is the same, nothing is changing here, and there is no spring in the system. Now let's look at the change of the internal energy. So the internal energy again equals to the friction force times displacement. And friction force equals to the normal force times coefficient of friction. What can we say about the friction force here in this, normal force here at this problem? Now it is not equal to mg. Yeah, it is smaller. Why? Because analyze this problem like with free body diagram, and you will see that there are now two forces acting up to the object. They are normal force and y component of this force, and also there is a force mg which is directed down, and their algebraic sum equals to 0 because there is no acceleration in y direction. And according to Newton's second law, if there is no acceleration, then net force equals to 0. So let me again recall free body diagram. Let's analyze the problem in y direction in order to find out this normal force. So according to Newton's second law, the force, net force, causes the motion with acceleration, and coefficient of proportionality is mass. So in our particular case, there is no motion in y direction. That's why net force y components would be equal to 0, total sum. Now, what are the forces acting in y direction if we introduce coordinate axis like that, coordinate system? So they are normal force plus y component of this external force. Here is y component, y. So this angle theta equals to this angle theta. So Fy component would be equal to F times sine theta. Agree? So plus F times sine theta minus mg equals to 0. So from that, normal force equals to mg minus F times sine theta. So we found normal force. So let's substitute it here. So from that, the friction force equals to mu times mg minus F sine theta. Okay. And from that, the change of the internal energy of the system equals to friction force times the displacement. So that would be d times this friction force, mu mg minus F sine theta. Okay. So what can we say about the work? Now we analyzed this final term in left hand part of the energy conservation principle. Now, what is the work? So work is now simply F times d times cosine theta. Agree? So in this problem now there is an angle. So we should integrate F dot product ds. So that would be just simply F dx times cosine theta. The integral will give us F cosine theta d. because integral from 0 to d of dx would be just d. So that's fd cos cosine theta. Now let's collect all together. So the change of kinetic energy, which is just T final, plus 0, the change of potential energy, plus the change of the internal energy, d mu mg minus f sine theta, equals to the work done by the external energy. So this is f d times cosine theta. Okay. So from that, let's express K final. It's equal to f d cosine theta minus d mu mg plus d mu f times sine theta. And it is given in the problem that we need to find the angle theta at which the kinetic energy is maximum. So in order to find out the extremum of this function, let's find the first derivative of this function with respect to theta. Then it should be equal to 0. And at the theta, when the first derivative is 0, that would be the maximum value. So let's find the first derivative kf with respect to d theta. It will give us, so this guy is minus f d times sine theta. So this part is not function of theta. So d theta would be 0. So plus d mu f times cosine theta. And since kf must be maximum, so this first derivative of kinetic energy with respect to theta must be equal to 0. So from that, we can say that this sum equals to 0. So it would be minus fd sine theta plus d mu f cosine theta equals to 0. So we can cancel fd here and here, and from that we'll find that tangent theta equals mu. So this is general solution for the problem. And in our particular case, with the given mu, so theta equals to tangent reverse of mu, and it is equal to 8.5 degrees. So that's the final answer. So it would have some optimum angle theta, because when we have this force applied at some angle, we reduce a little bit, or not a little bit, but we reduce the normal force. And because of that, we change a friction force. And obviously, that's why we lose less energy in the form of the internal energy. And our final kinetic energy will gain some more value. So we found that there is a specific angle theta at which kinetic energy would have maximum. Okay, questions, please? With this part? No? Okay, then let's solve next problem. Excuse me. Okay, next problem is, it looks difficult, but we will see now that it is much more easier to solve when you know the energy conservation principle, even you take into account the energy conservation principle. So the problem is as follows. A 10 kilogram block is released from rest at point A in figure. The track is frictionless except for the portion between points P and C, which has a length of 6 meters. So the block travels down the track, hits a spring of force constant 2250 newtons per meter, and compresses the spring 0.3 meters from its equilibrium position before coming to rest momentarily. Determine the coefficient of kinetic friction between the block and the rough surface between points P and C. So, okay, now we have this object which was positioned at the beginning, at this point, 3 meters above this level. It goes down. It passes this part of the track, which has 6 meters in length. Then this guy presses the spring, and when the spring is pressed to the maximum value, that is our final position of the object, and that is a final state of the system. Okay? Now let's collect what is given and let's solve the problem. So given, so mass of the object is 10 kilograms. Initial speed is 0. So the length of the part of this track with the friction is 6 meters. We have a spring constant here in the problem, it's 2250 newtons per meter. And the spring is now compressed by the displacement of 0.3 meters. I need to find friction, coefficient of friction at the part of the track which is not frictionless. So solution. So let's draw it again here. So here is a part of the track like that. So here we have friction. So here is the spring. Okay. So here we have a block positioned 3 meters above this level. So this is H, which is 3 meters. H equals 3 meters. So between points P and C, so they're just 2 points, B and C, the length is 6 meters, and we have a friction here. Excuse me, okay, like that. And then spring is compressed. So that's why we say that kinetic energy of this guy, potential energy at the beginning will be converted into the kinetic energy of the spring. So it will be compressed like that. And displacement of the spring equals to 0.3 meters. Okay, so now let's solve this problem. Again, energy conservation principle, the change of kinetic energy of the system, the change of potential energy of the whole system, plus the change of the internal energy of the system equals to the work done by the external agent. So by the way, here we can say that there is no any external agent acting on the system. That's why the work here is 0. So some object, some force placed this guy here, and some energy now is stored in the system. So no external agent here. So that's why the work would be equal to 0. But there is energy at the beginning. It would be converted into another form of energy, and energy would be conserved. That's how to apply this energy conservation principle in this problem. So now let's analyze change of kinetic energy. So what can we say? What was the kinetic energy of the system at the beginning, initially? Suggestions, please. Colleagues?
0.
0, thank you. And final, also 0, yeah, because it will not move. We are considering the moment of time when the spring is compressed by the maximum. What can we say about the potential energy in the system initially? So what was the potential energy at the beginning? So let's introduce the reference level here. So let's say this is y equals 0. So with respect to this level, the potential energy of the whole system was just potential energy of this guy. Agree? So that would be just mgh. So what would be the final, oh, not K. What would the final potential energy of the system? Suggestions, please.
Kx squared divided by 2.
Yes, thank you. So it's 1 over 2 K delta x squared. I just use delta x to show you that the spring is compressed. Okay, thank you. And now the change of the internal energy. So it is from definition equals to the force times the total displacement. The only part of the track with the friction is here. So that's why the displacement is 6 meters. So again, look at this object when it is placed at this part. You will see that normal force equals to mg. That's why the friction force would be equal to, so normal force would be equal to mg absolute value, not vector, but absolute value. That's why the friction force, which is equal to normal force times coefficient of friction, would be equal to mg times mu. Okay, so taking that into account, we can say that the change of the internal energy would be, so displacement times mg mu, mg mu. So that's it. There is no other type of energies here in the problem. So the total change of this energy would be equal to the work, which is 0 here. So the change of kinetic energy is 0 plus potential energy final minus potential energy initial, that is delta U, is equal to 1 over 2 K delta X squared minus MGH plus the change of the internal energy, that will be L times mg mu equals to 0, because work is 0. So from that, you can now express the coefficient of friction that we have to find. Okay, so mu equals to mgh minus 1 over 2 K delta X squared over mgl. So that's the general expression. Like that. And numerical value would be equal to 0.33 for this coefficient of friction. Okay, questions please on this part? No? Okay, great. Let's solve the last problem for today. So you can read this problem by downloading this document from the mail, because here it is not easy to see, but I will read it loudly. So two blocks are connected by a light string that passes over a frictionless pulley as shown in the figure. The block of mass m1 lies on a horizontal surface and is connected to a spring of force constant K. The system is released from rest when the spring is unstretched. If the hanging block of mass m2 falls a distance h before coming to rest, calculate the coefficient of kinetic friction between the block of mass m1 and the surface. Okay, so in the problem, we don't have some specific numbers, but it is given that there is a block of mass m1, there is a spring constant K, the system initially was at rest, so the object 2 has a mass of m2, so there is always also a final displacement of the object m2, which is h, and also let's connect equal acceleration. And with this information, we need to find coefficient of friction. Okay, so solution. So let's draw this again here. So we have a wall, we have the spring like that. We have a block with mass m1 here. So the surface now is rough. So the mass is m1. It was at the beginning. So it's like that. And here we have second object with mass m2. So they're connected with a unstretchable string like that. So here is a frictionless pulley. So that was at the beginning. So the spring was unstretched. Then we released the system, and this guy, because of the gravitational force, is now moved to a new position like that. So it's m2 here now. Obviously, because the spring is unstretched, this guy will move here to the new position of the object m2, and this spring would be stretched like that. Okay, so let's write here this h. So this is a height. Let's introduce the reference level y equals 0 here. Let's call it like that, reference level of the gravitational potential energy. So with respect to this potential energy, initial potential energy of this guy was mgh. So that's why it is easy to introduce like that. But you can introduce 0 level also here. It depends on your choice. Solution will be the same, the answer. So now let's analyze what is the energy conservation principle. So we have the change of kinetic energy plus the change of potential energy plus the change of the internal energy. So this is a change of the energy of the system equals to the work done by the external agent. So here, gravitational field is a part of the system. So we can see that there is no any external agent acting on the system. That's why the work done by the zero force is 0. So what can we say about the change of kinetic energy? The change of kinetic energy is 0 because initially everything was at rest, and the final position, when this guy moved down, this guy moved to the right, also nothing is moving. So kinetic energy change is 0. So potential energy. So let's talk about the potential energy. Potential energy. So what was the initial potential energy of the system? So this guy was unstretched. That means there is no potential energy stored in the spring. But this guy was above the position at rest. So that's why the initial potential energy equals to the gravitational potential energy for this object M2. Agree? So initial potential energy of the system equals to the potential gravitational potential energy of the block number 2. And at the final position of the system, at the final state, now it is at this level, which is 0. We introduce it like that. And we have this stretched spring. So let's introduce this displacement because of some force. Now it's stretched by delta x, this spring. So the energy stored in the system in the final point equals to 1/2 k delta x squared. Okay. Also, we have here friction, which means that we will lose some energy in the form of the internal energy, and numerically is delta E internal equals to friction force times the displacement, and the displacement is delta x. So it's the same as for the spring. Okay. And again, since normal force equals to mg here, so it's normal force, it's mg1 here, like that. So friction force would be equal to coefficient of friction times m1g times the displacement delta x. So this total change of energy equals to 0. So let's write this equation. So 0, which is delta k, plus final potential energy, it's 1/2 k delta x squared, minus initial potential energy of the system, which is m2g h, plus change of the internal energy, it's m1g mu times delta x equals 0. Okay. Now we don't know. So do we know what delta x is? Your suggestions, please. So look at this problem. So we need to find this mu. So everything is given except delta x directly. Delta x is not given. But can you say what is delta
Is
x?
it H? H?
Yes, this is h. Great. So we can just replace it with h. So that will be just 1/2 k h squared minus m2g h plus m1g mu times h equals 0. So you can cancel one h here, this h here, and from that we can express this mu. So mu equals to m2g minus 1/2 k h, this is spring constant, this is the height, over m1g. So that's the answer. And also there was a correct suggestion from the chat box. Okay, questions please about the problem. No questions? Any questions in general about the physics? If no, then thank you for your attention. Have a nice weekend. See you next week. Bye-bye.
Thank you. Bye.
Thank you.
Goodbye.
Thank you. Goodbye.
Bye.
Bye.